Thomson's experiment, the determination of the charge to mass ratio of the electron. In 1897, Joseph John J.J. Thomson performed some experiments with a cathode ray tube. The tube has a cathode, a metal electrode which produces the cathode rays, an anode with a hole in it through which the cathode rays pass, an electromagnet, and a pair of charged plates. Front of the tube is coated with zinc sulfide, which glows when a charged particle hits it. The cathode rays are really particles that carry a negative charge. When these particles pass through the hole in the anode and continue on with no magnet or charge on the plates, they pass straight through and strike the front of the cathode ray tube. A bright spot appears at B. If only the charged plates are turned on, the spot moves to C. If only the magnet is turned on, it appears at A. The shift is due to the fact that a force is being applied to the particles as they move between the plates or between the poles of the magnet. Thomson turned on both the plates and the magnet, and adjusted things so that the spot once again appeared at B. In this way, the particles were being acted on by two equal forces, an electric force from the plates and a magnetic force from the magnet. Because of the nature of the electric field formed by the plates, the electric force only acts on the particle while it is between the plates. Similarly, the magnetic force only acts while the particle is between the poles of the magnet. The amount of deflection caused by the charged plates depends on four things: the amount of the charge on the plates, the charge on the particle, the mass of the particle, and the speed of the particle. The charge of the particle and the charge on the plates produce the electric force on the particle. The greater the force, the greater the deflection. The greater the mass of the particle, the less acceleration is produced by the force. Remember that force equals mass times acceleration, so the less deflection there is. And the faster the particle goes, the less time the force acts, so the less deflection there is. Similarly, the deflection caused by the magnet depends on four things: the strength of the magnet and the charge of the particle, which determine the magnetic force, the mass of the particle, and the speed of the particle. We can easily measure the charge on the plates and the strength of the magnet, but we cannot measure the charge on the particle, the mass of the particle, or the speed of the particle, all of which influence the deflection. However, when we combine the magnetic force and the electric force from the plates so that the forces are equal, the speed of the particle becomes irrelevant, and we are left with the mathematical relationship that involves the charge-to-mass ratio of the particle, Q over m, where Q is the charge of the particle and m is the mass of the particle. If one tries different metals for the cathode, the same charge-to-mass ratio is produced, which strongly suggests that we are getting the same particle, which is the electron. It has a very large charge-to-mass ratio, Compared to the previously determined charge-to-mass ratio for an ionized hydrogen atom, the charge-to-mass ratio for the electron is nearly 2,000 times as great. This means one of two things. Either the charge of the electron is much larger than the charge of the proton, or the mass is much smaller. If we use the charge of the electron discovered by Millikan in 1908, along with the charge-to-mass ratio found by Thomson, we find the mass of the proton is about 2,000 times the mass of the electron, and is about the same as the mass of a hydrogen atom.